Hi, in this video we will discuss the trigonometric substitution. Before we continue, please recall that previously when we differentiate the inverse function for sine, tangent, secant, or the cos, cotangent, cosecant, we found that we are able to get something in rational function which has the component a squared plus b squared. Right, you can see all of the term here is a squared plus b squared form. And we say that on the right hand side here is a redundant information where you can see same answer, but this is in negative and this is positive. So these three derivatives are very useful for the application of integration because it provides new antiderivatives such as the trigonometric substitution. In practice, let's say you have a problem like integrate 1 over 1 minus x squared square root of it. Okay, to solve this problem, we can use the trigo substitution. For example, x is equal to, by referring to this proof 2.1, 1 minus x squared is relevant to sine, so we can let x equal to sine x with a constant a. There are three options that we can choose here. Either you can choose the trigonometric substitution, x equal to a sine angle, or x equal to a tangent angle, and lastly x equal to a secant angle. So since cos, cotangent, cosecant, they are redundant as shown in this relationship, so we do not use it in this study. We only choose the first two. These are some important remarks for the trigo substitution. To master this topic, you must know the important trigonometric identity. So you must know the relationship for tangent, sine, cos like this. Cotangent, secant, cosecant is the reciprocal for tangent, cosecant, and sine. These are the three identities that you must always remember. And then we have the add and subtract identity here. And then we have product of sine cos function here, and we can convert this product into summation or subtract. And for this identity, we can convert the product sine x into double angle formula. And if we have something in sine square or cos square, we can convert it into double angle cos. You need to master the important derivative and integral as well. So for example, in this case, you have to know the integration for sine, cos, tangent, cotangent, secant, and cosecant. So make sure you know how to apply this. And also you have to master the derivative for sine, cos, tangent, cotangent, secant, cosecant here. So these are all basic derivatives and integration. Normally I will remember these three terms. So I know the differentiate sine, I get cos. Okay, I use the relationship sine with cos. Okay, cos I get sine, and positive I get negative here. Okay, so I don't need to memorize it. Okay, I can use the relationship to derive the answer. And for this case, tangent, the relationship with cotangent, secant with cosecant, right? So positive here, you get negative here. And for the second relationship with cosecant, secant with cosecant, tangent with cotangent. So positive becomes negative here. Same observation can be observed here as well, where if let's say I remember integrate sine, integrate tangent, and also the secant, then you see the negative become positive for all of the equation here. Cos becomes sine, tangent becomes cotangent, and secant becomes cosecant here. Before you proceed with the trigonometric substitution part, please make sure you master all the important trigonometric identities as well as the important derivative and integral. In this topic, you all should remember First of all, you have this substitution x equal to a sine angle. Second, you have a tangent angle. Third, you have a secant angle. So when should we use this? When you have integrate this function with respect to x-axis, then you can use x equal to a sine angle. So when you have a constant in front minus with the x square, you should use this substitution. On the other hand, if you have integration of a constant square plus x square, so if this is the case, then you use x equal to a tangent angle. Lastly, if you have dx square minus with the constant square, then you use the case for secant. So the angle has the range for each cases like this. There's a typo for this constant. Please tell me to correct it. The angle here should be less than pi over 2 instead of 3 pi over 2. So remove the 3 here. First of all, to understand why the angle for the sine is between negative pi over 2 to the pi over 2, let's look at this figure. This is the figure x equal to sine angle, where you can see that at angle equal to 0, you get your x equal to 0 here. So the x can be from negative infinity to infinity. However, if you take the inverse, where your angle equal to inverse function for the sine, so in this case, you can see that the range is from negative pi over 2 to pi over 2. So that's why we have this range. So by using the same approach, you can see that for the inverse function tangent, the range for the angle is from negative pi over 2 to the pi over 2 here. So that's why you have the range is equal to this. So the last case is the second. So for the inversion, the angle should be within, if you look at this table, this figure, sorry. So it should be from 0, x equal to 0 here, to x equal to pi here. So this is your range. However, at here, which is pi over 2, your angle is not equal to pi over 2 here. So this is the condition. Therefore, in the note, you can see that your angle except pi over 2, okay, it should be from 0 to pi. So if you understand the previous 3 substitution for trigonometric, which is sine, tangent, and secant. So let's start for the application. So for the first case, we want to solve this. Okay, integrate square root of 1 minus x squared. You can see that the coefficient here is a squared plus b squared. So if you see this format, there's a high chances that we can apply the Trigo substitution. So in this case, let's say you apply the normal substitution. So let the t equal to square root of 1 minus x squared here. If you differentiate, you get this. And we try to substitute. And you found that this method, it becomes more complicated than the original one, right? So the normal substitution is not working here. In this case, we can use the trigonometric substitution, x equal to a sine angle. Because we have this form in a square, which is the a is the constant, minus with the x squared. So if you see the constant minus x squared, then you use the sine form. So the a squared is equal to your 1, so that we can get a equal to 1, you get sine angle. So this is your substitution. So we differentiate dx over the angle, you get the cos angle here. From this relationship, sine angle, so let's say we form a triangle, and then this is your angle, and then x over 1 give you the sine angle. So we can form this relationship, and to find the distance here, we can simply use square root 1 square minus x squared, which is this term. And you can see that this is exactly the same component that we have here. So from this triangle, you can find all the basic trigonometric functions. For example, you can find the cos. So the cos angle is just taken the square root 1 minus x squared here divided by 1. Therefore, you get this. Sine angle, which is x over 1, like this one. So tangent angle, okay, is x here divided by this distance. So you can also find the second. Second is 1 divided by cos, right? So cosecant you also can find by using 1 over sine and then cotangent as well, where you can find from 1 over tangent. So you can find these 6 trigonometric function, but from this triangular. So let's make the substitution into the original function here. You should be able to get this. So this is your original integral. So after you substitute x equal to sine angle, you get this. So your dx is equal to cos angle d angle, which is this part. And you should know that 1 minus sine square angle, based on the identity, is a cos square angle. So the square root and cos can be cancelled, you get cos. Cos multiply cos, you get cos square angle. So cos square angle can be simplified into cos 2 angle by using this identity, where you can see that your cos square angle will be equal to, so 1 you move on the left hand side, you get cos 2 angle plus 1, okay, and then you divide by 2. Therefore, we can form into this. Lastly, cos you can integrate easily. Cos becomes sine, and don't forget, differentiate 2 angle, you get to divide by 2. So 2 multiply 2, you get 4 here. And 1 over 2, you get 1 over 2 angle. And lastly is the constant. So everything here is in angle. You have to back substitute by let the x equal to sine angle inside, right? So this term is equal to inversion of sine x. And then for this term, sine 2x angle, you can find from the identity sine 2 angle is equal to 2 sine angle cos angle, where your sine angle is equal to x here. You substitute. So your cos angle based on this, you can substitute square root 1 minus x squared. So you have 2x square root 1 minus x squared. Therefore, we can substitute inside this function. And we divided it by 4. So 2 here can be cancelled. At the bottom, it becomes 2. So this is your final result. So we can check. Okay, so the first term is from here. And this term is obtained from the second component. Right? So this is our final result. There is an extra remark for this problem. So for the same problem here, previously we told you that the substitution x equal to square root 1 minus x squared cannot be applied because it will make the thing more complicated and cannot be solved. So we have to let x equal to trigonometric substitution. So here we can see a square constant minus the x squared. So from this relationship we know that the x must be sine angle. And the constant a square is 1 here, therefore your a is 1. So 1 multiply sine angle is sine angle. So we can just remove the 1. So your x is equal to sine angle. However, as we told you before, so for this problem, the sine, okay, and cos is actually just redundant information for the sine, right? So instead of just substitute the x equal to sine angle, actually we have another option, which is substitute x equal to cos angle here. So let's try with this example. Okay, so we have the trigonometric substitution by using the x equal to cos angle.
So dx over d angle in this case is negative sine angle, where based on this relationship you can form a triangle. So you have 1 here, x over 1 is your cos angle. So with that you can form the 1 minus x square here. So your sine angle is the distance here divided by 1, which is this. So your cos angle is the same here. Your tangent angle will be this term divided by the x, right? So you can form this relationship as well as the secant, cosecant, and cotangent based on this. So by using the same approach, we substitute the x equal to cos angle inside. So x equal to cos angle, you get cos square here. So dx is negative sine angle d angle. We substitute here. Based on the identity, 1 minus cos square angle is equal to your sine square angle. Sine square angle can be cancelled with the square. Here we have sine. Sine multiplies sine here, you get sine square. So the negative we can bring out because it's a constant. Then we can use the double angle identity to reduce the sine square angle into cos angle, cos 2 angle. So look at this function, sine square angle will be equal to, we bring the 1 minus to the left hand side, we get 1 minus cos 2 angle and divided by 2. So it's very important that you're familiar with the identity so that you know when to apply it. And then you can substitute this, and 1 over 2 after you integrate, if we just straightforward, you can get angle over 2. So because you have negative here, we put it here. And on the cos part, cos you get sine, okay, the negative and negative become positive. So you differentiate the two angle here, you should divide by 2. 2 multiply 2 here, you get 4. So this is your constant. And we back substitute since your x is equal to cos angle, right? So your angle will be equal to inversion of x. So we can substitute inside, you get the first term called inversion of the cos x. So for the sine 2 angle, okay, is equal to the 2 sine angle cos angle. So your sine angle is this, you can substitute inside. And then your cos angle is this, x. So after you substitute, you divide it by 4, you should be able to get this term. And don't forget your constant. So you see that from the same problem, you can define it, the x equal to sine angle or x equal to cos angle to find the answer. So for the first case we show you, okay, we get this answer. For the second case, you get this answer. You see that one, okay, you get inversion sine x. The second one, you get negative inversion cos x. So when we plot the graph, you get the one in blue color and red color here, where you see the shape is similar, just that they are differentiated with a constant. Okay, so in case these two are the same answer, just that the constant C1 and C2 here, they will be different. So based on this observation, we can see it's the same pattern, and there's a offset by some constant here. If the constant C1 and C2 are known, they will become the same answer. So in this study, this should be your focus. Please use the x equal to sine, tangent, and secant only. Don't use the one cos, cotangent, and cosecant. So although this also give you the same answer, okay, since it's a redundant information, so in this study we do not apply these three substitution, but we only focus on these three. Okay, so this is your some extra information for your understanding. Let's try with more example here. So in this case, if let's say you don't know, you try with the substitution method, you let x, okay, equal to, you let the t equal to square root 9 plus x squared, dt over dx, you get this. After you substitute, okay, you found that the term become more complicated. So normal substitution is not working here. So if you found this case, what we can do is we can see that there is another pattern which is a squared plus b squared. So let the b to be x lah. Okay, b squared. A squared plus x squared here. So if you see some relationship like this, your substitution x can be equal to a tangent angle. Okay, tangent based on the plus here. And your a square, okay, your a square is 9, therefore your a is equal to 3 here, right? So 3 square become 9. So we can continue by using this substitution. So this is our trigonometric substitution. Let the x equal to 3 tangent angle. So dx over the angle, okay, remember differentiate tangent, you get the secant square. So from this relationship, x over 3 is the tangent. So you can draw a triangle and then x over 3 is equal to your tangent angle, where you can get this distance. So this distance is square root 3 square plus x square. This is this term. So by using the relationship for sine angle, you can get the x over square root, okay, for the 9 plus x square here. For the cos angle, it will be 3 over the square root term here, plus the tangent angle, which is what you have here. So we continue. So we can substitute this inside the original function. You should get x squared to be tangent square angle. So your dx will be 3 secant angle d angle. Okay, from here you substitute. After that, 1 plus tangent square angle is equal to secant square angle. Therefore, you can reduce into this form. And square root here can be cancelled off. Then you get secant angle here. So this part is square root of 9, you get 3. So this gives you 9 secant angle. So 3 multiply 3, you get 9 here. Secant angle multiply secant square angle, you get this term. So let's continue. So previously we get this, and you can see that you have a function secant angle, secant square angle here, where we can easily integrate the secant square angle to be tangent, right? Because if you differentiate tangent, you get secant square angle. So we can use the integration by part, okay? And normal substitution is not working here, okay? So we let the u equal to secant angle, dv equal to secant square angle d angle. So u differentiate it, you get secant. dv you integrate, you get the b equal to tangent angle. This is the hint where for the integration by part, we always choose the dv to be something easier to be integrated, right? So if you integrate the secant, yes, you can continue, but integrate secant give you something in ln, which is much more complicated. Therefore, we let the dv equal to secant square here. So you know that integration by part, it will be uv minus v du for the secant power 3 angle, d angle. So we can substitute the uv minus v du inside. So 9 multiplied with secant tangent, okay, 9 multiplied with negative term here. So we can see tangent and tangent here become tangent square, and secant remain. So from here, okay, tangent square angle and secant angle looks like complicated, So we try to use the identity where you should know that 1 plus tangent square angle is equal to your secant square angle, right? So let's try to convert the tangent square angle. Okay, you should get tangent square angle, you move to the right hand side, you get this term, secant square angle minus 1. So we can expand this. Okay, second multiply inside, you get secant power of 3. Second multiply 1, you get secant angle here. So you see this term secant to the power of 3 here. So we can move to the left hand side for this term. And you should get, this is a 9. Okay, we have negative 9 here. And then you have a positive 9 here. So you move the negative to the left hand side, you get positive 9. So 9 plus positive 9, you get 18. Right? So this term remain. This term will remove to the left hand side. And for this term, negative negative become positive. 9 multiplied secant, you get this. So we continue with this. Okay. So from the previous problem, you can see that we have a secant. Okay, integrate secant here. We want to solve this. So you can use the appendix to solve it, or you can use derivation. So secant angle you multiply with this thing because you want to get secant square and secant tangent here. As you know, when you differentiate the secant, you get secant you get secant square. Differentiate the tangent, you get secant square. So this is a form that when you have some term inside here, when you differentiate this term, let's say this is your t to be the second, in this case we let u equal to this term, okay, and then du is, after we differentiate the u here, okay, let the u here, so this will be your du, right? So we can substitute, okay, this thing, we let the substitution u equal to secant, we have this, and then we integrate, you get the ln u plus a constant, where your u you can back substitute, you get back the secant angle and plus tangent angle. So this is your result for integrate secant. So you don't need to do the derivation as you have the appendix. It gives you the direct answer, right? But if you understand, you don't need to memorize the formula. You can directly use the integration, okay, to solve it. So we have the equation here previously, and now you already get the integrate secant, so we can just substitute this inside, and therefore you get this answer. And the 18 here, let's say we move to the right hand side, so 9 divided by 18, you get half, right? 9 divided by 18, you get half also for this term. So for these two terms, you get half. So therefore, this is your answer. And you see that this is for square root secant to the power of 3 angle, D angle. Right? So previously, this is the problem that we are going to solve, and then we are able to get it to be this answer. And later, we solve the 9 secant to the power of 3 angle to be this answer. And what we want to find is x is in the answer of x function, not the angle. Therefore, we have to do the back substitution. So you have secant here. Secant is 1 over cos. So secant is equal to 1 over cos. Therefore, you should get this. Okay, before I move this, let's try here. Secant is equal to 1 over cos. You should get this term 9 plus x squared over 3, right? So you can substitute inside the secant. So your tangent is x over 3, you can substitute here. Second, same here, you can substitute inside. Tangent also, right? So we can continue. So we substitute inside, this is called back substitution. So this is the answer that you have. So if you stop here, you should be able to get the answer, okay? And you can further simplify the answer, okay? By let all the constant together, you should get 1 over 2 here, okay? And then on the right hand side, you can, since the denominator here is the same 3, so you can add the nominator at the top, right? So it can be further simplified. But if let's say you stop until here, okay, I know that you are able to do the integration well. Let's look at the example 3. So now we have another situation here where your x squared is in front, you minus with your a squared, let's say. So if you see term like this, okay, same thing, you found that the normal substitution is not working. If you have this relationship, okay, you can use the trigonometric substitution where we can let the x is equal to a second angle. So second is when you have the x squared in front, you minus with a constant square. So your a here, okay, since your a squared is 4 here, so your a will be just equal to 2. So we continue, okay, you have this. So second is also 1 over cos, so you can write into this form as well. So when you differentiate, you get 2 second tangent. So cos angle is equal to x over 2 over x here, right? So from this relationship, you can get this. So we can easily plot a triangle. So your cos angle is 2 over x. So 2 over x is here. Okay, you get the cos angle. Therefore, you divide this distance divided by the x here, you get the sine. Tangent is taking this distance divided by 2. Okay. Let's substitute the x equal to 2 seconds inside this, and then, okay, x equal to 2 seconds. So let me write it here. X squared, you should get 4x second square angle. So the dx is 2 second angle, tangent angle, so we can just substitute here. Then from here you can see that you can take out the 4. So you have the second square angle minus 1. So this is, we can use the identity where this term is equal to the tangent square angle, which is this. Then we continue. Okay, so the tangent can be cancelled off. You get tangent only here. Square root of 4, you get 2. So the 2 here, multiply with 2, you get 4. And then tangent, multiply with tangent, you get tangent square. Second remain. Let's continue with this. So previously we want to solve, okay, this thing. If we separate the term here, you can see second tangent here, where you should familiar that if you differentiate the second, you differentiate this, you should get second tangent. So if you integrate the second tangent, you get the second, right? So this is like, okay, we can multiply these two components. Okay, we can use the integration by part to solve this case, where we will find that normal substitution is hardly to work in this case. But actually it's still working, just that you have to find a way, okay, to reduce the tangent square angle into the more basic function like tangent, secant, cos, sine, which is not so straightforward, but you can use it. Okay, you can use the substitution by using more identity. Okay, trigonometric identity, convert this into more basic form. Okay, however, in this case, it will be just straightforward for us to apply the integration by part. As we mentioned earlier, we let the dv equal to secant tangent. We want to integrate it. So you get the v equal to secant, because in the differentiate secant, you get sec sine. So we have to let the u equal to tangent. Okay, so du equal to secant square. So this is our integration by part. Secant angle, tangent square angle. This component is computed by uv minus v du. So this is your u, this is your v, and this is your v, this is your du. So from the right hand side, secant to the power of 3 angle. So we have performed this earlier and we get this result. You can just substitute inside. Right? So this is our left hand side. We get this. For tangent secant, this is the term here. So minus with this thing. So you have to minus with this term. And you can multiply the 4 inside. You get this term. Okay, multiply 4 with negative 1 over 2. You get 2 here. Right? So minus 2 you multiply inside. Right? So this should be negative as well. So please correct it. So this should be negative. Because you multiply 4 inside this thing, it should become negative 2. Negative 2 multiply this, you get this term. Negative 2 multiply ln, you should get negative 2 here. Right? So please help me to correct. This is the result that we obtained so far. Okay, let me revise it. Okay, initially you have this component, you want to solve this integral, and then we know that we have to let x equal to 2 secant, which is the trigonometric substitution. After you substitute inside, okay, you get into this form, and you continue to integrate. Now you can simplify this term into this now. So this answer is in tangent. Okay, second, where you should continue, okay, to do the back substitution to get back the x. So here we perform the back substitution. So this answer, okay, we want to simplify it for the tangent. You should substitute this tangent inside here. For the second, it should be 1 over cos. So 1 over cos is x over 2. So this is your second. Okay. So substitute inside here. So second here, okay, use this. Tangent, use this. Second, okay, and tangent also, use these two. So substitute this information inside, you should be able to get this term. So if you able to do until this step, okay, you get a correct answer for the integration. So you can further simplify this, okay, by multiply all the constant together, you should be able to get this final answer. In summary, for a problem that you cannot solve by using the normal substitution, if you found the term here, which has the a square minus x square, so, or you found the term like x square plus a square. Lastly, here you have x square minus a square. In this case, okay, you should know for the first case here, constant minus is to be something in sine, and your a square is 9, so you should have 3 here. For the second case, it should be in tangent because it's positive. And last case, it will be secant. And be careful, the a square is 6 here, so your a here is square root of 6. A square here is 15, your A is square root of 15 here, right? So you must know how to form the triangle here, because this only tell you the side. If I want to know the tangent, cos, cotangent, cosecant, and also the secant, okay, I have to form this triangle. Okay, please make sure all of you know how to do this. Okay, you may try this example by using the following trigonometric substitution.